Okay, so some of our rules were what?
X equals R cosine theta.
All right, so we noticed that if I took cosine of theta, that gave me x over r, and then we multiplied both sides by r. So one of our conversion formulas was x equals r cosine theta. And similarly, we had y equals r sine theta. Okay, so we primarily use these formulas when we were given the polar form, when we were given r and theta. These two formulas allowed us to very quickly and very easily convert to rectangular form. All right, and then we had two other formulas.
R squared equals X squared plus Y squared.
R squared equals x squared plus y squared. That's just our regular old Pythagorean theorem. That's nothing new. And then I think we had tangent of theta was y over x. So typically we use these formulas when we're given x and y and we're trying to find r and theta. So there's really four formulas, but they're used for different things. These two are used when you know r and theta and you're looking for x and y. And then these two are usually used when we know x and y and we're looking for r and theta. All right, so give me a point. What's that?
Rectangular or polar?
Oh, I don't care. Give me a point in polar or rectangular. I don't care. You get to pick a point.
3-1.
3-1. Is that polar or is that rectangular? That's rectangular. All right. So let's say I gave you the point 3, 1, and this is rectangular. And I asked you to convert this to polar. What would you do? You could draw a triangle, okay? So 3, 1 is right here. So this distance is 3, that distance is 1. Then what? You can find r. How do you find r? Pythagorean theorem. So r squared is x squared plus y squared. So r squared is 9 plus 1. So I guess r is the square root of 10. And then how would you find theta? You could use cosine, but typically we would use tangent. Typically we would use tangent because we can use the 1 and the 3. We can use the information that was given to us. So theta, or tangent of theta, is 1 over 3. I don't think so. Because we're going to have theta equals arc tangent of 1/3. And unfortunately, I don't think that's one we know. We know arc tangent of square root of 3. And we know arc tangent of square root of 3 over 3. But I don't think we know arc tangent of 1/3. So what are we going to do? You have two choices. Choice number 1 is type it into your calculator. Choice number 2, leave it. Just like that. That's a perfectly acceptable answer to me. All right, so our answer would be 3, 1 in polar form is square root of 10, arc tangent of 1/3. So let me ask you a question. Because we drew the point 3, 1 and we drew the triangle, did we really need to memorize any of those four formulas? I don't think so. Would it be a bad idea to memorize them? No, probably not. But I think if you simply draw the point, draw your triangle, I think you can figure it all out from the triangle. So that's what I would do. Now we did have to be a little bit careful. We talked about this the other day. This point was in quadrant number 1, so we didn't have any problems. When we use this arc tangent thing, arc tangent always gives answers in which quadrants? 1 or 4. So what did we have to do if this original point we were given was in 2 or 3? We had to add or subtract 180 degrees or pi radians if you prefer to use radians. So do watch out for that. Because this point is in quadrant 1, our arctangent does give us the answer in quadrant 1, and everything's good. We don't have to worry about it.
So if it was in 2 or 3, that's the way to make sure to subtract or add.
Subtract or add. Typically we add, but you could subtract. Subtracting works also. Typically we would add 180 degrees or add pi radians, one or the other. Okay, so conversely, give me a polar point. Give me an R number. 6. And give me an angle. Let's not use 90 degrees. 90 degrees is too easy. Why is 90 degrees too easy? Let's just do it. We'll do it. It's too easy, though. Again, I think I would start by drawing the point. Where is the point? R is 6. Theta is 90 degrees. It's right up here, isn't it? So it's right here, 6, comma, 90 degrees. So what's that in rectangular coordinates? 0, comma, 6. Yeah, so that one's an easy one. You don't need any formulas at all if you draw the point. So if I give you 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees, anything that ends up on an axis, those are really, really easy. You don't need any triangles. You don't need any formulas at all. All right, so give me another R value. What is it? Negative 5. Oh, I like that one. Negative 5, and then an angle that's not on one of the axes. Pi over what? Pi over 6. All right, I like that we're using radians. That's exciting. Pi over 6. All right, so where is the point negative 5, comma, pi over 6? Which quadrant is that in?
No.
3. That is correct. All right, because remember how this works. My angle pi over 6 is actually in quadrant 1. So here's my angle pi over 6. But what do we do when this R is a negative number? We don't go this direction, we go that direction. So we're over here. So this is the point negative 5, comma, pi over 6. It's over in the third quadrant. But again, I think you could simply draw your right triangle, like so. This is X. This is Y. You have a right triangle. In this right triangle, what would you know about X in relationship to this negative 5 and in relationship to that angle? Negative 5 is the hypotenuse. So if I wanted X, I could use X as adjacent, and this is hypotenuse. So I could have cosine of pi over 6 is adjacent over hypotenuse. So again, if you draw the triangle, I don't think you really need to have the formulas memorized. Why is negative 5 the hypotenuse? Because Jimmy said he wanted my R value to be negative 5. He picked it, not me.
Oh, it's the R.
It's the R value, yeah.
It's a polar.
It's a polar point.
Yeah.
Correct, it's a polar point. So the first, in a polar point, the first number is always the hypotenuse, and then the angle. So I'm going to multiply both sides by negative 5. So X is negative 5 times, what's the cosine of pi over 6? 3 over 2. And then I would do exactly the same thing with Y. And what's going to be the only difference when I use Y? I'm not going to have cosine, I'm going to have sine. So Y is going to be negative 5 times the sine of pi over 6. And the sine of pi over 6 is 1/2, so that's negative 5/2. Questions on that? All right, so the last thing we really didn't talk about the other day, we talked about converting points from polar form to rectangular form and back and forth, but we didn't talk about converting equations. So I might give you an equation in rectangular form. There's an equation in rectangular form. X squared plus y squared equals 16. Anybody know what that graph looks like if I were to draw that equation? It's a circle. Why is that a circle?
Squared plus y squared.
When you have x squared plus a y squared, that's a circle. Where's the center of this circle? At the origin, what's the radius? 4. Square root of that number. All right. You don't really need to know that to answer the question. The question is, I want you to convert that to polar form. How do you do that? Instead of x's and y's, I want r's and thetas. Do what? 16 would be 4 squared, and that would also be the radius. We just said this was a circle with radius 4, right? So what's the equation of the circle in polar form? What is 4? R.
Radius.
4 is not an equation. It needs an equal sign in it.
R equals 4.
R equals 4. Why is this R equals 4? Remember, our Pythagorean theorem said r squared equals x squared plus y squared. So if I want to convert x squared plus y squared into polar form, x squared plus y squared is r squared. So this is the equation in polar form. R squared is 16, and I can do square root of both sides. The radius is 4, which makes sense. If this is a circle of radius 4, it makes sense that the equation is radius is 4. Of course not. Well, all be that easy, right? How about if I gave you y equals x squared plus 3? What's that graph look like? Not a line. The parabola. Why is that one a parabola? Because that was an x squared, but it does not have a y squared. That one's only got an x squared, but not a y squared. That's a parabola. How do you write that one in polar form? I can move the y over. I don't know how I'm going to get that y squared out of that, though. All right, so let's remember our list of formulas here that I told you really don't need to memorize. Now I'm going to tell you probably should. One of our conversion formulas was r squared equals x squared plus y squared. What was our other formulas? X equals r cosine theta, and y was r sine theta. So if I want to take this equation and write it in polar form, instead of y, I'm going to write r sine theta. So where there's a y here, I'm going to write r sine theta equals, instead of x squared, I'm going to write r cosine theta squared. R cosine theta squared plus 3. There's that equation in polar form. That's it. That's not too bad.
So we're just making one equation now?
Uh-huh. Now, what we do like to do if we can, and I don't think this one's an easy one to do it with, I'm going to rewrite this as r squared cosine squared theta plus 3. Generally, when we write equations using x's and y's, we like to get y all by itself when we can. When we write polar equations, a lot of times we like to get r all by itself when we can. Is there an easy way to get r all by itself in this problem? Well, but if I divide the sine theta out, I'm going to have r here, but I'm still going to have r on this side. If I divide by the r, if I divide by r, I have to divide by r here, and divide by r there. So that's going to put an r on bottom. That's even worse. That's a bad thing. Is there an easy way to get the r all by itself? No, I don't think so. So for this problem, we're not going to. Can it be done? Probably. And I'll tell you how you would do it. I'm going to write 0 equals r squared cosine squared theta minus r sine theta plus 3. So what did I do? I moved that r sine theta over to the other side. Anybody have a clever way that I could get this r all by itself now if I wanted to? What if this equation was written this way? R squared times 9 minus r times 4 plus 3 equals 0, and I asked you to solve that equation. What would you do? There's no like terms. That is a quadratic equation. Normally we would write it as 9r squared minus 4r plus 3. So how could you solve this quadratic equation?
Factor.
You could try factoring. I don't think this one factors. Use the quadratic formula. This is a quadratic equation. You have r squared, you have r, and then you have a number. You could use the quadratic formula with a being cosine squared, b would be sine, and c would be just the number 3. The quadratic formula would still work. So if I was in a really, really mean mood, and I told you you have to get the r all by itself, that's what you would do. You would use the quadratic formula. It would not be pretty.
So when you just converted it, how come you get like r sine, like instead of r cosine, like first?
Because up here I had y,
Okay.
and my conversion formula is y equals r sine.
Okay.
So anywhere I saw a y, I wrote r sine. Anywhere I saw an x, I only saw one of them, I wrote r cosine. All right, so let's deal with an easier one where we can get the r all by itself pretty easily. How about 2x plus 3y equals 5? If you were to graph that, what kind of equation would it be? What kind of picture would it be?
Line.
That's a line. Why is that a line? There's no squares, there's no cubes, there's no square roots, there's no fractions, there's nothing mean, is there? All right, so this one's just a line. Convert it to polar form, what would you do? All right, so instead of x, I'm going to write r cosine theta. Instead of y, I'm going to write r sine theta equals 5. Now, how can I get the r all by itself? I can factor an r out, so I can write this as r times 2 cosine theta plus 3 sine theta equals 5. And then to get the r all by itself, I divide. So r is 5 divided by 2 cosine theta plus 3 sine theta. So when you're dealing with a line, which one looks prettier? The equation in rectangular form or the equation in polar form? Rectangular looks much nicer. Why does it make sense that a line is going to look much nicer in rectangular form than it does in polar form? Because polar is based on a circle, based on the angle, and rectangular is based on a rectangle over and up.
Are we gonna have to convert it in other, like in polar form?
Oh yeah, that's a wonderful question. So her question is, will I give you polar equations and you have to give me the rectangular back? Sure, why not?
It's not like I brought it up, it was a magical idea.
It was the very next thing I was going to do, so it's not like she was being mean or anything. R equals sine theta. There's a polar equation. I want it in rectangular form. All right, so let's write down our formulas again. R squared equals x squared plus y squared. Y equals r sine theta. X equals r cosine theta. What do you do? Any good ideas? Do what? You said do something with the R. I just couldn't hear you.
I just say try to move the R over.
Try to move the R over. I could move the R over. I could subtract R on both sides. Don't think that helps though.
Square both sides?
Close. Squaring both sides would help. On the left-hand side, I would have an R squared. An R squared I could switch, couldn't I? But on the right, I would have a sine squared, and what would I do with the sine squared? I don't know. But you're close. R would be equal to the square root of x squared plus y squared. That's true. What am I going to do with that sign? I really wish I had an R squared right there. How can I get an R squared right there besides squaring both sides? Multiply by R. How is that going to help? If I multiply by R, that's going to give me an R squared there. And it's going to give me an R sine over there. And R sine is a fancy way of saying Y. So there's a very, very common technique. If I give you polar and you want rectangular, quite often you're going to multiply by R to give you an R squared and to give you the R sine that you want. So we're going to multiply both sides by R. That gives me R squared equals R sine theta. R squared is x squared plus y squared. And R sine theta is y. So that's the equation x squared plus y squared equals y. What kind of graph is that? It's still a circle, but it's no longer centered at the origin because of this y over here. But it still has an x squared and a y squared. It's still a circle. It's no longer centered at the origin. It's the only difference. It's centered somewhere else. Questions on that one?
So you just, the R squared is equivalent to x squared plus y squared, and the y was, alright,
Yep. All right. Let's do a hard one. R equals sine of 2 theta. That's a hard one. Any clever ideas? Well, double angle formula, wonderful idea. That's 2 sine theta cosine theta. Okay. So I do use that double angle identity. Now what? Multiply both sides, but that's going to give me R squared equals 2R sine theta cosine theta. We're very, very close. R squared is x squared plus y squared. R sine theta is y, but what am I going to do with that cosine? We're really close. Can't divide it out. I really want another R right there, don't I? Okay, so I'm going to put one right there. If I want it, I'm going to put it there. What's the penalty for putting an R on the right-hand side? I got to multiply the R on the left-hand side. So that's going to give me an R cubed. All right. On the right-hand side, I have 2. What's R sine theta? Y. And what's R cosine theta? X. What am I going to do with R cubed? How am I going to take R cubed and convert it to X's and Y's? I'm going to take out an R, and I'm going to write it as R times R squared. And then just a minute ago, we said R squared is... So what's R? The square root of that. Except when I do square roots, what do I need to remember? How many square roots are there? There's 2. There's a plus or a minus. So this R right here, this is plus or minus the square root of x squared plus y squared. This R squared is x squared plus y squared equals 2xy. So there's the same formula written in rectangular form.
So we always just make R plus or minus.
If you have just a single r, you can always make it plus or minus the square root. That is correct. All right, so this time, which equation is prettier? The original polar equation or the rectangular equation? The polar is a whole lot nicer. What's this graph look like? Remember I drew some of these on the calculator the other day? This was a flower. This is a 4-petal rose. So this one, I think, I'd have to grab my calculator. I think it looks like this, roughly. It might be rotated 45 degrees. I don't remember which way it looks.
Could you explain one more time how you made the square root of x squared plus y squared, like that left side?
Back up here, we have r squared equals x squared plus y squared. So if I want to get the r all by itself, what would I have to do? I have to do square roots, and when I do square roots, I need to remember there are two of them. There's a positive square root and a negative square root. All right, so we looked at some pictures the other day, and we realized that sometimes like a graph like this would be difficult to write in rectangular form because it loops around on itself and it's not a function. Well, there it is. There's what that would look like in rectangular form. Much, much, much easier to write it in polar form. Now imagine if the teacher were in a really bad mood and he wrote r equals sine of 3 theta. Think of how much, we're not going to do that one, by the way. But think of how much harder it would be because we wouldn't have this nice double angle formula. We'd have to deal with a whole bunch of things in order to convert it to rectangular form. It would be very, very ugly when we got all done. Questions?